Hello everyone, welcome for joining us. So today we invited Yu Haoding to give us a talk about the safe reinforcement learning in the presence of non-stationarity theory and algorithms. Yu Haoding is currently our fifth-year PhD student at the UC Berkeley Operations Research Department. His research interests include reinforcement learning, control theory, optimization, statistic learning. During his PhD, he focuses on non-stationary sequential decision-making problems, such as time-varying optimization, the global convergence of process gradient methods, and non-stationary reinforcement learning. Hi, Yuhao. You can start your talk.
Oh, thanks so much. So can everyone see my screen?
Yes.
Oh, great. Okay, firstly, I would like thank Shanding for the warm welcome. And it's my great honor to have this opportunity to present our recent work on the safe reinforcement learning in the presence of the non-stationarity. Yeah, so during the presentation, please feel free to interrupt me if you have any question. So for today's presentation, I will first start from the motivation and introduction of why we are interested in the safe RL under a non-stationary environment. And then I will talk about our recent work on the three different scenarios for this problem, which are the non-stationary constraint MDP, the non-stationary risk-sensitive control, and the meta-safe reinforcement learning. And then, if we have time, I will talk about some future directions and the future ideas for the future projects. Okay, so reinforcement learning has been one of the hottest topics in AI by demonstrating its capability on attaining the human level performance in video games, beating the champion Go player, and more recently discovering the novel, efficient, and provably correct algorithm for the fundamental tasks, such as matrix multiplication. However, unlike this simulation-based system, such as a video game or Go, in many applications of autonomous systems, the existing reinforcement learning techniques are not yet applicable or are too risky to deploy due to the safety requirements. For example, the collision avoidance in the self-driving cars, the resilience requirement of the power network, the robustness of the medical treatment, as well as the risk management in the financial market. And in addition to this safety assurance, the underlying environment may undergo changes and be non-stationary, such as the electricity demand in the power system and the autocorrelation of the daily returns for S&P 500. It is also mentioned in the seminar book by the Richard Sutton, who is regarded as the father of RL, that non-stationarity is the case most commonly encountered in the reinforcement learning. And our project is motivated by this pressing need to provide computational tools and analytic assurance for the reinforcement learning in the non-stationary environments under the safety constraints. And in particular, we will consider the interaction of the agent with a non-stationary environment, which provides not only the reward signal, but also the feedback on the safety requirement. The safety constraint feedback will require the agent to avoid the bad states or the bad actions while doing the exploration. In addition, due to the time-varying nature, this reward and safety constraint signal may also be time-varying, and therefore the agent is not only unaware of what is bad ahead of time, but also needs to keep updating their beliefs on the safety requirement, because what is bad is also varying over the time. And in this presentation, we will consider two types of non-stationarity. The first one has a non-stationarity within a single task, such as designing a controller to distribute and regulate the power network where the electricity load demand is time varying. The existing algorithm designed for the stationary environments cannot learn very effectively. This motivates us to design algorithms which can incorporate the detection or prediction of the future non-stationarity into the decision making. The second one considers multitask learning with clear task boundaries, such as robot manipulator, which tries to continually learn to serve the tea, move the box, or clean the house while satisfying the safety constraints with human in the loop. Due to the similarity of these tasks, the learning process should be significantly accelerated if the robot manipulator can leverage the prior experience for the new coming task. This motivates us to design a mechanism to adaptively update the safe policy initialization so that each new task can be learned very effectively from the given initial policy. And in summary, this project aims to develop a set of computational tools with a rigorous analysis for the design of safe RL in the presence of non-stationarity. In particular, we will consider the non-stationary constraint MDP, non-stationary risk-sensitive RL, and also the meta-safe reinforcement learning. And this table with the color-coded marks indicates the extent to which the existing methods address the corresponding issues, and compared with the relevant research directions, our work is the only one which addressed all aspects of the difficulties, such as the multitask learning, non-stationary environment, safety requirement, and theoretical guarantees in the non-stationary safe RL. Now I will start with the details of the projects we did towards the realization of the non-stationary safe RL. The first formulation we consider is the constraint MDP. In the constraint MDP, we consider an episodic setting where at the beginning of each episode, the agent is reset to an initial state S1 and takes an action A1, receives the corresponding reward and the cost feedback, and then move to the next state. And due to the non-stationarity of the environment, this reward and cost feedbacks may vary episode by episode. So they have a superscript M, which denotes the episode of the CMDP. And in each episode M, the agent aims to maximize the expected total reward while satisfying the constraints on the expected total cost via the formulation of the constraint CMDP. And if the data is non-stationary, it makes sense to make our decision based only on the most recent data. That is, we need to forget the outdated data, such as using the restarting, such as using the forgetting-based principle, like the restart estimation, using a slide window, or the exponentially decayed weights to estimate the time varying model. Then a key question is, how often shall we forget the outdated data? The intuition is that if the non-stationary level is very high in a given period, then we may need to discard the outdated data more often and vice versa. And therefore, a key notation variation budget is introduced in the non-stationary RL to measure the total non-stationary variation in the environment given a period. And usually to achieve the optimal performance guarantee, the forgetting frequency, such as how often should we restart the model estimation, needs to be carefully designed, such as that the restart frequency is a sublinear term of the total variation budget, like it is equal to the order of the b to the power of alpha where alpha needs to be carefully designed. And suppose that the agent executes policy pi I m in the episode m. We now define the optimality gap as the difference between the value of the optimal policy for each episode and the value of agent's policy for each episode in the long run over the entire capital M episodes. And the constraint violation is defined similarly. And in this work, we design an algorithm called restart optimistic primal dual PPO. And in particular, we use a restart policy evaluation and the restart policy improvement to handle the non-stationarity of the environment, and use the optimistic value estimation for the exploration, and using the dual update for the safety constraint satisfaction. And the key challenge is how can we incorporate these three components together to achieve the safe exploration in the presence of non-stationarity with the theoretical guarantees. And to address this challenge, we consider two different scenarios separately. The first scenario assumes that each constraint is uniformly feasible and the agent has access to the local variation budget. The local variation budget is defined as the total variation of the environment parameter within each epoch, where the epoch itself is defined as a time interval between the two restarts of the model estimation. So the first set of assumptions has a weak requirement on the safety constraint, but it requires more information on the non-stationary environment, in the sense that it requires us to have the local information of the variation budget. On the other hand, we also consider a slightly stronger condition on the safety constraint. That is, the safety constraints are uniformly strict feasible, in the sense that there exists a positive constant gamma such that there exists policy pi such that all the constraints are strictly feasible with respect to this positive constant gamma. And due to the stronger condition on the safety constraint, we can relax the requirement on the non-stationarity, for which we only assume access to the total variation budget over the time period that we are interested in. And we now analyze our algorithm based on these two alternative assumptions. And to stabilize the dual update under the non-stationarity, we will first consider the regularized Lagrangian function, which has additional regularization on the dual variable, mu. And we use the projected gradient ascent to update the dual variable. Under the assumption of the uniform feasibility, the dual variable can be very large. That is, this upper bound of the dual chi can be potentially unbounded. And therefore, we need to have the dual regularization and additional knowledge on the local variation budget to stabilize the dual update. And on the other hand, if we have a slightly stronger condition on the feasibility, that is, the constraints are uniformly strict feasible, then the dual variable is well bounded. That is, this upper bound chi is guaranteed to be a finite number. And therefore, the dual regularization and the local and additional knowledge on the local variation budget is not needed. And we studied the proposed algorithm under the two alternative conditions that require different amounts of knowledge on the constraints. And the results are summarized in this table, and both methods enjoy the dynamic regret and constraint violations, which are sublinear in terms of the number of episode M and the total variation budget B. And this is the first provably efficient algorithm for the non-stationary CMDPs with safe exploration. And in our paper, we also extend these results from the tabular MDP to a function approximation setting. And finally, we verify our method on a simple numerical experiment where we consider a grid world with the time-varying goal states and the obstacle states. And the red curves are corresponding to our method, which apparently outperforms the baseline method without considering the non-stationarity when doing the safe exploration. And in addition to the safe requirement in the form of the constraint MDP, we also consider a different kind of safety requirement, which is a risk control. And in the risk-sensitive reinforcement learning, we will consider a mean variance optimization, in which we not only want to maximize the expected accumulated reward, but also want to control the level of risk, which is measured by the variance of the accumulated reward. And our goal is to learn a risk-sensitive policy, which can adapt to the non-stationary environments. That is, some parameter of the environment may still vary episode by episode. However, the variance of the accumulated reward is very difficult to estimate in an online environment because for each environment, we only encounter a single trajectory. So to address this issue, we take the Lagrangian function of this constraint problem and find it is related to the Taylor expansion of the entropic risk measurement of the accumulated reward, which means that if we take a Taylor expansion of this value function under the entropic risk measure, it is equal to the expectation of the accumulated reward plus the beta times the variance of the accumulated reward. So if you regard this beta as a penalty term or the dual variable in the Lagrangian function, this Taylor expansion is approximately equal to the Lagrangian function of this mean variance optimization problem. However, such formulation is still intractable due to the nonlinearity and nonlinear coupling of this log operation expectation and this exponential operation. And therefore, it is still difficult to obtain the unbiased samples for this term. And to further address this issue, we take the exponential transformation on both sides. Instead of working directly on the value function under the entropic risk measure, we can work on the exponential of the value function, which is apparently straightforward to sample and estimate. And for this formulation, we propose two methods based on the knowledge of the variation budget. So if the variation budget is known prior, we can use the forgetting-based method, which we discussed in the previous slides, such as restart estimation or sliding window or the exponential dilated weights, and apply these techniques on the exponential value function. And the restart frequency is also carefully designed based on the knowledge of the variation budget to minimize the dynamic regrets. However, the variation budget is usually unknown in practice. And therefore, we want to propose an algorithm which can adaptively detect the non-stationarity of the exponential value functions. The idea is that if we can detect the event that the observed regret is abnormally larger than the promised bound in the stationary setting, then we can detect that there must have some non-stationarity of the environment happen.
Hello, Yiha.
Yeah.
How can we get the variation budget? What is the variation budget here? Variation budget.
Yeah, so variation budget is what we present here. That is it is a measurement of the total non-stationary variation in the environment given a period M.
Okay.
So,
Thanks.
for example, in some case, you may have a good estimation of the how the system will vary, over the last, for example, 100 or 200 episodes. So, in that sense, you have if you have a good estimation of the variation budget, then you can use this forgetting-based method to design an optimal forgetting frequency.
Okay.
But usually this good estimation of the variation budget is not always known. Therefore, we want to also propose a method which does not require such prior knowledge, which is what I'm going to talk now.
Okay. Thanks.
Yeah. So in the scenario where this variation budget is unknown, what we want to do is that we can design a non-stationary detection mechanism based on the observed regret, and the theoretically promised bound. And for example, in the risk-sensitive RL, we can upbound the dynamic regret by the following two terms. The first term measures the difference between the exponential of the optimal value and the exponential of the our value estimation. And the second term measures the difference between the exponential of our value estimation and the exponential of the true value of the current policy. And luckily, if the environment is stationary, we have very clear promised bound for the R1 and R2 terms. For example, if the environment is stationary, we can know that R1 should always be non-positive, and R2 is bounded by a term which is proportional to the square root of the number of total episodes. So if we can directly observe the R1 and R2 and compare it with its promised bound, we can use that as a detection of the non-stationarity. For example, if we find that R1 is greater than 0, then it means the promised bound is violated, which means that the underlying assumption for this promised bound is violated, which means that this system is not stationary. And once we detect that the system is not stationary, we can restart our estimation of the system. However, the challenging part is that this term, which I highlighted using a blue box, it cannot be directly observed because we never know the true optimal policy in advance. So to address the challenge that the first term R1 cannot be directly observed, we can fully utilize the optimistic estimator property of our policy evaluation. So optimistic estimator, as its names imply, it always provides optimistic estimation of the value function, which means that at any time in a stationary environment, this optimistic estimated value function should always greater than the optimal value function shown by this blue curve. And this is what we mean by an optimistic estimator. And when the non-stationarity happens, for example, if the non-stationary happens so that the optimal value function jumps up from this level to this level. And because of the optimal value function, optimal value increase, if we learn in this new environment, our observed value will also gradually become larger and larger since we are learning the optimal value in this new environment. And gradually, this observed value will exceed the previous optimistic estimator, which indicates that non-stationarity must happen. Because in a stationary environment, the optimal value or our observed value should always below this optimistic estimator. And whenever this crossover happens, it helps us detect the non-stationarity of the environment. And after the detection of the non-stationary environment, we can restart our estimation of the environment, of the model. Yeah, so based on this two mechanisms on handling the non-stationarity based on whether we have the knowledge of the total variation budget, we propose two algorithms. The first one is the restart-based algorithm with the knowledge of the total variation budget. And the second is the adaptive detection-based method, which does not require the knowledge of the total variation budget. And the restart-based algorithm requires the knowledge of the total variation budget so that it is not parameter-free. And on the other hand, adaptive-based method is parameter-free. And once insightful conclusion is that the risk control and the handling of the non-stationarity can be separately designed if the variation budget is not a prior. What I mean by separately designed is that we can handle the non-stationarity and the risk control separately. That is when we design this restart mechanism by deciding how frequent shall we restart our estimation. This restart frequency does not depend on the risk-sensitive parameter beta. However, on the other hand, if we are applying the adaptive detection-based algorithm, the non-stationarity detection depends on the risk control parameter, and therefore their design are always coupled and cannot be separated. And finally, we move to a setting where we have multiple tasks with a clear task boundaries using the idea from meta-learning, which meta-learning has widely been used as a learning-to-learn framework to solve unseen tasks with limited experience. And in particular, in this session, we will study what we call the meta-safe reinforcement learning framework. And in this work, we studied the problem of the meta-safe reinforcement learning through the constraint CMDP within online framework. And each within task solves a constraint MDP problem in this upper box. And the meta-learner aims to sequentially update the meta-initialization for the future new task, given the knowledge of the land-safe policy on the previous tasks. And the goal of the meta-safe reinforcement learning is to design a mechanism such that the task average suboptimality gap and the task average constraint violation is minimized. So in this matrix, we are taking the average over the total number of episodes or total number of tasks. And for each task, we measure the difference between the value of the optimal policy and the value of the learned policy. And the constraint violation is measured similarly by comparing difference between the benchmark and the value function corresponding to the cost for the given learned policy. And the expectation is that this performance measurement should improve as we solve more and more similar tasks, because we can learn from the similar prior experience for the future task. And to solve each within task CMDP, we focus on a method called constraint rectified policy optimization, CRPO. It is a pure primal-based online CMDP algorithm which switches between the reward maximization and the safety satisfaction. In particular, it will perform the objective optimization when the constraints are all satisfied, and it will perform the constraint minimization if there is a violated constraint. And the main property of this method is that it doesn't require to involve the dual variable. And therefore, when we do the meta-initialization, our meta-learner does not need to learn the meta-initialization for the dual variable. And therefore, it becomes the out-loop meta-learning much easier. And under some mild conditions, this algorithm also enjoys a provable guarantees on the suboptimality gap and constraint violation. And we can observe from this upper bound that the task average performance guarantee and constraint violations are upper bounded by terms based on the distance between the optimal policy and the initial policies. If the initial policy is very close to the optimal policy, this upper bound is supposed to be very small. And the crux of our idea is to utilize this upper bound and design a meta algorithm that can sequentially update the initial policy pi 0m for each task by performing the online learning on this promised upper bounds. So in the ideal setting, if all the parameters in this upper bound, such as pi star m and mu star m, which represents the optimal policy, and the corresponding induced state distribution for each task, if these parameters are known, then this upper bound can be regarded as a convex function of the initial policy. And then we can consider this function fm of the initial policy as the individual loss function in an online convex optimization setting, and apply the method such as follow the regularized leader to sequentially update the initial policy for the future new task. And in the meta-safe reinforcement learning framework, we expect the task average optimality gap and the task average constraint violation to improve with the similarity among these online CMDP tasks. And we now discuss the notations of the similarity in the static environment. And given the optimal policy for every task T, the task similarity can be measured by this term, which measures the difference between the optimal policies and a single best initial policy in hindsight. So comparing these two scenarios, we can see that the second scenario has a smaller task similarity, since all the optimal policies for different tasks are more closer to each other. And this notion of task similarity in the static environment is natural for starting the gradient-based meta-reinforcement learning, as it implies that there exists a best meta-initialization in hindsight with respect to which optimal policies for individual tasks are all close together. And with this measurement of task similarity, we can present our main results as shown in this blue box. In the ideal setting, where we assume that we have knowledge of all the required parameters, we can show that our meta-learning framework is able to guarantee that the task average optimality gap and constraint violation is proportional to the task similarity, which means that if the tasks are very similar, then we should learn very efficiently, and with the guaranteeing on the safety requirement also. And this result reveals the benefit brought by including more tasks with more similarity. And our result is also the first to establish such relationship in the meta-safe RL, or even for the unconstrained case. Now we want to extend the previous result in the ideal setting to the more practical setting where we only have access to the inexact estimation of the required knowledge. In our framework, the meta learner only requires the inexact optimal policies for each within task CMDP and the corresponding induced state visitation distributions estimated using the collected offline trajectories to conduct the upper bounds, to construct the upper bounds on the suboptimality gap and the constraint violations. And in addition, we can also adaptively update the learning rate for each CMDP task. That is, this learning rate, which is denoted by the notation alpha m, can also be adaptively learned such that we can adjust this learning rate for the upcoming new tasks to make the learning more efficient. And the idea is similarly, we can still regard this upper bound as a convex function of the learning rate and then apply the online convex optimization algorithm to sequentially update the learning rate for the upcoming new task. And finally, in the ideal setting, we compare our learned policy initialization sequence with a single best initial policy in hindsight. However, in many settings, we have a changing environment in the sense that the competitor sequence or the sequence or the policy initialization we want to compare is varying over the task. And in this case, it is natural to study the dynamic regret and compares with a sequence of potentially time-varying initial policies. And our method also has a generalization for this more practical setting. And finally, in the numerical experiments, we demonstrate the effectiveness of our proposed meta-SafeRL method and compare with some popular baselines. These baselines include follow the average leader, the simple averaging, and the pre-trained and random initialization of the previous policy initializations. And follow the average leader basically use the average of the initial policies from the previous tasks to adaptively update averaged initial policy for the upcoming new task. And the simple averaging use consider all the trained tasks and use the average of all the initial policies from the previous encountered task as the initial policy for our testing task. And the pre-trained method just use the optimal policy we learned from the previous task as the initial policy for the upcoming new task. And in our environment setup, we will generate different tasks using different parameters of the CMDP, and we will run all the algorithm online where tasks are encountered sequentially, and the results we are going to present are just for the testing task with specified policy initialization methods. For example, in the simple frozen lake example, where we have the different locations of the orientation and hole, which give us the different SafeRL tasks. And when the task similarity is low, we can observe that the meta SafeRL achieves higher rewards and lower constraint violation much more quickly than the base initializations. And when the task similarity are very high, which means that all the tasks are all very similar, we can observe that the baseline, pre-trained, and the follow average leader are also competitive with meta SafeRL in terms of the reward maximization and the constraint violations. And the good performance of these baseline methods can be explained using the fact that as the test task and the training task are all very similar, the policy initialization will also be very close to the optimal policies of the testing task. And we also demonstrate our method using the Acrobot, which is a two-link robot open engine, which has a continuous state space. The agent is rewarded when it achieves a certain height of the end link. And two constraints are introduced for the two links. And we randomly generate 50 different tasks with different mass links and the center of the gravity. And similarly, we can observe that for the Acrobot environment, the meta-safe RL achieve higher rewards quickly and zero constraint violation as compared to other baseline initializations under either low task related settings or the high task related settings. And similarly, we demonstrate our method using the half-cheetah environment and the humanoid environment. And because of time reason, I will just leave these details. And in summary, this project develops a set of computational tools with a rigorous analysis for the design of safe RL algorithm in the presence of non-stationarity. And in particular, we consider the non-stationary constraint MDP, the non-stationary risk-sensitive RL, and the meta-safe reinforcement learning framework. And based on our current results, the future investigation includes incorporation more accurate detection and prediction of non-stationarity, and also get the agent to adapt the safety adapt safely without forgetting the critical strategies or the critical safety requirements learned from prior tasks. And we also want to generalize these results to a set of formulations beyond the metrics of the accumulated reward to include the scenarios like the imitation learning or the pure exploration task, etc. And finally, we want to design a set of benchmark problems and case studies to evaluate the developed algorithms. And I would also like to discuss some details of these future directions. The first one is continual balancing among the constraint and objective, which is a very unique challenge in the safe non-stationary safe RL, because in the non-stationary safe RL, we want to continuously, our goal is not just to singly optimize a reward. We need to balance between the constraint violation and the objective maximization. And this is more challenging when both of them are non-stationary. So the limitation of the proposed prime-module-based method for the non-stationary CMDP is that the optimal dual solution is time varying in a non-stationary environment, which makes learning and safe exploration more challenging. And what if we can use a pure prime-module-based method like this CRPO paper we discussed in the meta-safe RL framework? And if we can, can we propose a pure prime-module-based method for the non-stationary CMDP, which can dynamically balance reward maximization and safety satisfaction more smoothly without the need to update the time-varying dual variable? And the second idea is that how can we deal with address the triad of the exploration, exploitation, and prediction in the non-stationary environment? So we all know the trade-off between the exploration and exploitation in the standard RL, but in the non-stationarity, with the non-stationarity, we also need to consider the prediction of the future environment. So for example, if we consider an episodic RL with the reward varies over episodes, and the standard reactive-based a popular method to address this is to construct an estimated reward based on our previous experience. And usually we will have, for example, if we are using a linear model to estimate the reward, we can have this kind of reward estimation, where the beta tau is some parameter, and this window WT basically specifies the number of data you will use from the previous experience for the future prediction. And in the most of the reactive-based method, this parameter beta t is just the simple average. It just takes a simple average of a window near to the current time to make an estimation. However, what if we can use our proactive based method which we actively forecast the future? For example, we use some forecaster to forecast this reward to build a model and then make a decision. And finally, it is important to balance the performance in the past and in the future to avoid the catastrophic forgetting with a safety constraint. So what we discussed are also forward directions in this talk, which we want to have the future learning to have good performance on a future task. However, in a backward direction, we want to avoid that our agent forget how to perform safely when a very similar task reappears. Right, so a naive idea is that we can use this episodic memory and the gradient rotation to guarantee that for each new task, we satisfy the constraints that encountered in the past. And that's all I have today. And thank you very much for your attention. And I'm happy to take any questions. Thank you.
Okay, thanks to Yuhao's great talk. Hey guys, any questions?
Hi, Yuhao.
Hey.
Yeah, thanks for the great talk. So I think you currently consider non-stationary in an episode-wise setting. So basically, it means that the non-stationary will happen between the episode, between different episodes. So, but I think another type of non-stationary may happen within an episode. It's kind of like a time step-wise. So do you have any idea about how to detect those non-stationary happens within an episode, and how to address this kind of non-stationarity?
Yeah, that's a good question. So, so actually, the within episode non-stationarity is kind of easy to address in the episodic setting, because in episodic setting and in episodic MDP with finite horizon, you can always use this backward-based method, right? You and have this time-dependent or time step dependent policies, right? Like the most standard Bellman backward approach for the finite horizon MDP, right? You can do this to address the within episode non-stationarity for the episodic MDP. But I think what you may really mean is that what if we have an infinite horizon MDP?
Yeah.
Right. And where we won't have this chance to reinitialize our trajectory, and we need to we need to encounter or we need to interact with agent in a setting where we are not able to reinitialize. I think in this case we can still obtain the similar result, but we will require some knowledge or some assumptions on this infinite horizon MDP. And some standard assumption in the literature is that it requires something called the mixture of this MDP. That basically means that you need to guarantee that your MDP allows you to return to the some state or some specified state within some time. So I think with this requirement on the infinite horizon MDP, you can have the similar results.
Okay, thank you so much.
Thank you.
Hello, any question? So I think maybe the non-stationary CFR may be very useful for ML, safe ML, because one important feature MRA is non-stationarity. Yeah, I think, yeah, maybe we can work together later.
Yeah, I think the multi-agent RL is a natural setting where, from each agent's perspective, they are facing a non-stationarity, but this non-stationarity is inherent, is implicitly generated by other agent instead of the environment itself. So I think I'm always very curious, can we apply this non-stationary RL-based method to address multi-agent RL? Because for each single RL agent, it's like it's facing a non-stationary environment. Right? So, if we can independently, so can we design a independent and decentralized policy learning for each agent in this multi-agent system by, borrowing the idea from the non-stationary RL and also utilizing this special structure of the non-stationarity in the multi-agent RL setting, to learn to learn policies for the multi-agent RL.
Yeah, I think it's maybe important problem. Yeah, I think maybe we can discuss it in detail. Maybe we chat or and work on the topic.
Yeah.
So, guys, any question? If maybe we don't have any question, maybe we can end the talk. Yeah, thanks for your joining us to talk. Yeah.
Thanks so much.
Okay, so have a nice day. See you.
Thank you. Have a great day. Bye bye.
Bye-bye.